Last night, my crazily smart teenager said a calculus problem took her over an hour to figure out. Well, naturally, I got curious. And when I got my hands on the problem, I had to laugh because that same problem is the one I used to put on the final to test my students. And it has to deal with the application of implicit differentiation. It's a new concept. And it's kind of like a new pair of shoes. I love shoes. And there's always a breaking in period where shoes looks great, but can you really wear and look and walk and look great in it? So here's the problem. Find the slope m of a line if this line passes through the origin and is tangent to a curve. Of course, the first thing, I hope by now, listening and studying the differentiation, you know I'm asking you to do the differentiation. However, where does the curve fit in and why is the tangent line? I love on the finals when my students give me sketches because that shows me they're thinking and then they're trying to fit their new shoes in and trying to walk around and trying to break it in. So let's go through that same process. Let's draw this curve. It's a natural log curve. It breaks down at x equal to 0 and cross x-axis at half because natural log of 1 equal to 0. So here's my curve, look like half the shoulder. And I'm going to try and attempt to draw a tangent curve that through the 0, 0 and tangent to the curve on the shoulder somewhere along the way. Here's my line and here's my curve. I don't know where this tangent curve intercepts the curve, the tangent point is. I'm just going to call it a beta 0. Of course, by now I'm hoping next hint or next milestone is how do I figure out beta 0? Because if you go from this here onward is how do I figure out beta 0? You're on the right track. It's kind of wearing the shoe in the house and trying to break it in. Let's keep on going. Let's do this implicit differentiation. That's the easy part. We're going to take this natural log of 2x through the implicit differentiation. I do have another video on implicit differentiation, the good, the bad, the ugly. So if it's not a familiar topic, you're more than welcome to look it up. For now, I'm just going to speed up a little bit. I need to do the 1 over 2x. I'm plugging in the formula and the 2 after the 1 over 2x comes in from the implicit part because I have to take derivative of the 2x one more time. That's where the implicit differentiation comes in. You have to treat it as a nested Russian doll. Anyway, so the slope is 1 over x, and depend where my x or my interesting point is, the slope will change, of course. Since we're curve or the line we're particularly interested in go through 0, 0, the equation, the formula for the line is pretty easy because it's y equal to mx. I don't have to deal with the y-intercept. So slope changes according to what point I'm looking at. And for this particular one, I named that point beta 0. So y equal to mx is my line, and m as dy dx evaluated at the point of interest x equal to beta 0. And I'm going to plug the info in there. And here is the trick. Can you be courageous enough, and even though you don't know where beta 0 is, can you use the differentiation, the new pair of shoes, try it on and walk it anyway? Okay, walk it on the runway. And from here, here's the elegance of the problem shows in, because regardless what that beta 0 is, for this particular problem, a particular curve and particular tangent line, I do not need to know because y is equal to 1. Now once you get there, hopefully you get a smile, because if y equal to 1, this point is shared by both line and curve. I'm going to use that information y equal to 1. I'm going back to my curve to find my beta 0, because beta 0 and 1, that point shared by the line and the curve. I can use two pieces of information to find that. Using the y equal to natural log of 2x, going back there, I find beta 0 is actually a number. It's e over 2. Okay, e is just our natural log. It's a constant. All right, kind of like a pi 3.14, so on and so forth. Now, in order to find m, one more step, y is equal to mx. Since m is equal to 1 over x, since I know what beta is, beta 0 is the point where the line and curve intercept. It's the x-coordinate of that intersection point. And from there, easily I go back to see m is equal to 2 over e. Now, this problem does look pretty involved. Let's have an overlook to see what we actually did. We did a sketch to see, okay, I have two curves. I'm looking at the intersection point. I'm going to use this new pair of shoes called differential equation, or implicit differentiation, pardon me. And I find the slope, dy dx. And then I use the line to say, all right, since it's a line, I know what the slope is. I don't know what beta 0 is, but I'm going to use it anyway. And I found out y turned out to be a constant of 1. And since the point is shared by both line and the curve, I go back to the curve to find where beta 0 is. And then one more step is beta 0 is 1 over m. And from there, I solve the problem. All right, so hopefully this new pair of shoes, after this big long runway, we're able to use it and fit it in and break it in and becomes part of our calculus wardrobe. All right, this is Dr. Pan recording from Tucson, Arizona. I invite you to share or comment on this video. Join me. Together, we can make math easy again.